Okay, whew, let's get to classifiers. So a classifier, at least for logistic regression, is really just sticking a sigmoid on the end of the linear regression model. So I have some input vector with a number of features, and I'm going to do a transformation on it down to a one vector. And then I'm going to threshold it and get a probability of it being class one, and that's what this threshold does. And so there's my classification. And so I've taken the well-known toy data set, the wine classification data set, which is normally a three-class problem, and I've broken it into class just 0 and 1. Okay, so this is nothing more, logistic regression is nothing more than a one-layer network with a sigmoid activation function. And it gives me this separating line here that is a best fit, for like the max likelihood of the fit. And how do I make the model? Well, it's exactly as it did before. The only difference is instead of in between layers having a nonlinearity, well, I'm also going to have that, but here I have a nonlinearity on the end, the sigmoid. And so this is how we simulate a logistic regression model. That is what you're familiar with, and graphically, architecturally, it looks like this. And so this is straight from the notebook that I guess we'll do the next time. And so you can actually draw things this way to get a feel for how things work. So as we did before, actually, yeah, there's a link to it if you want to go to it earlier. I haven't cleaned up all those notebooks yet, but the code is there. So as we did with linear regression, we can add more power to this thing by adding more layers and by adding more neurons. Okay, and then by the way, I know that all these details are fuzzy. I'm just trying to give you the 10,000 foot view. And then as we start to go through the notebook, you'll start to get a more and more concrete feel for it. All right, so I'm going to add more neurons and another layer. So this is my previous model, you can think of it as, and then I'm sticking this thing on the front. And now I'm going to say, all right, I've got two, let's see, make sure, yeah. So I've got two features. I've got proline and alcohol. These are characteristics in the wine data set. And I'm going to convert that 2 vector into a 3 vector. So what's in the third dimension? I don't know. Like we did with word vectors, right? We used 300 vectors to represent a word. What's in each dimension? We don't really know. But somehow it represents the semantics of that word. And so that's all we're doing here. Okay, so, and by the way, that's how you can get word vectors, is you just train a model with an embedding layer, and it'll give you those things. So all we're doing is transforming a 2 vector to a 3 vector, run it through a sigmoid, run it through another layer, and run it through a sigmoid, and this gives us a classifier. So we've got to make sure that there's a sigmoid on the end to get a 2-class classifier out of this thing. And so the code for this is a layer, a nonlinearity in between, another layer, and then it must terminate with a sigmoid to get the particular classification. Now notice, look at the difference here. With a single layer, all we're able to get is a separating hyperplane. But if I add more power to this model, it's highly nonlinear. And look at this cool, smooth, groovy surface I've got there. I think this is a much better fit than the simpler model. Okay, well, let's go crazy. Let's add a lot more. So I've got the 2 input vectors, proline and alcohol. And now, I don't know, what is it called, that 10? I don't know. Oh, it is 10. So now I'm going to create, instead of a 5 vector, I'm going to create a 10 vector. Run it through the nonlinearity, run through the final layer, get a prediction. And now I even have a non-contiguous region. So not only is it not limited to a hyperplane, it has the advantage that there can be multiple regions that are of a particular class. So you can see this is not contiguous with the other region. This is like, Hawaii, and this is the mainland United States. So And is this a good separating surface? I don't know. I think this is kind of overfit, right? I kind of like this one. To the human eye, that looks pretty good to me. But of course, when you're just playing around with a complex model, you don't have the luxury of looking at it as a human. There's just too much data, too many dimensions. But anyway, so this is the code. Now, of course, this is not saying how to train it. We'll do that part too. But this is how you construct the architecture of this neural network. So I'm hoping that you're seeing, look, it's just linear and nonlinear building blocks that I'm gluing together. And I can make linear regression. I can make logistic regression. I can make really complicated versions of those with really powerful surfaces just by how I combine them. Okay, so if I'm building a classifier, again, I need that sigmoid on the end because I want a probability out of that. A ReLU is not bounded, right? It can go all the way up to infinity, but a sigmoid is not, and that's what I need for a probability. Okay, however, I can still use the ReLU non-linearity in between my layers if I want. And so when I trained this model, I didn't get quite a curve, but I did get kind of a curvy surface. So it's kind of an approximation of this, just doesn't look quite as good. But it also allowed me to jump in here and grab that little one. And, it looks like it kind of went around the corner there and got that little blue one. So this one looks like it probably fit the training data even better than the previous. And I can guarantee you with these ReLUs in there is a lot faster to train than the sigmoid. Okay, because the sigmoid is just, is it this, 1 over e, 1 plus e to the minus x or whatever, and that's, work to compute, whereas a ReLU is just a clip. Okay, now let's move from a 2-class problem to k classes. So here is a standard regression model, a logistic regression model. And remember, I've got 3 really beautiful features that were made for me magically by the previous part of the neural network, but this is really just logistic regression. If I want to have a problem that is not just, say, cat or dog, I want it to be cat, dog, horse, and, lizard, then I need something more complicated in the back than a simple linear regression. Well, all I have to do is stack these things. So if I have 2 classes, I can get away with sort of output 0 or 1 here. Now what we do is I convert this last layer to have k neurons. And each one is going to give me a strength, an indication of my confidence that it is class 0, class 1, class 2, class 3. And then I'm going to run it through this fancy thing called a softmax, which I'm visually representing by a sigmoid with k on. And we'll see what that looks like in just a second. But look at the difference here. I've got 1 value coming out here, and then I threshold it, and boom, I've got a probability. What happens here is I've got k values coming out of my last layer. It's like just getting, for a typical logistic problem, you would just have 5, if you have 5 output classes, you could just have 5 logistic models, right? That's basically what we're just doing here. And then what we do is we look at them all together, and we get a probability or likelihood associated with each class into a vector. And then we can choose the largest of this to tell us what class to predict. So let's look at this in a little more detail. So all I'm doing to move from 2 to k is changing the back end of this model. Okay, so as I said, we don't have just 1 neuron in the last layer, we've got k. And instead of that sigmoid, we have to use something a little more complicated, which is the softmax function. And this looks a little weird at first, but think of this e to whatever the output is. The output could be, 2. It could be 45.6. It could be whatever. I'm taking the exponent of that, and I'm looking at the ratio of it to the overall sum of those values. So let's pretend for the moment that this is sort of like the mass, or represents the likelihood or confidence we have in a particular class. And I'm dividing it by the overall confidence we have in these things, and that just kind of normalizes it. And what this looks like, it's useful to get just like play around with these values. So I got these just random values I picked as output to some neuron, to 3 different neurons. Got 3 neurons outputting 3 different values. If I take the e to each one of these, I get this. That's just e to the z. So I get, it magnifies this one, a little bit of this one, and this one doesn't move much. And then if I take the sum of all those guys, that's 148 plus roughly 3, right? But I just do this division, and look how it nicely lays this out as a set of confidences or probabilities. So this function just happens to work really well. I'm sure a mathematician can tell you something delicious about, you know, e to the z. But in my mind, I think of it as how much of this confidence am I consuming relative to the total? So you can think of it as how much more confident am I in a particular class? Yannet is
so just it's an easy way of taking any number and making it positive, so then you can normalize it.
Yeah, right. So if this were -1, it would just be a small number, right?
Yeah. So yeah, I think that the way to think about it is like, if you want to normalize, you have 3 numbers and you want to make them into probabilities. The first thing you have to do is to kind of make them positive.
Yeah.
And then you have to like, divide by that. This also has the effect that it is kind of like a max. That's why it's called softmax. Because if you see that the 5 gets like a lot of the probability in comparison to the other 2 numbers, then you can think about it as that's why it's soft max, because it's almost like a max. You know, the 5 is getting most of the probability.
I got you. Yeah, it's allowing one of them to get the lion's share, the most of it. Okay, I got it. Cool.